When people first learn about database indexes, they often assume databases use binary search trees. After all, binary trees give you logarithmic lookups. But databases have a completely different optimization target. They're not minimizing comparisons. They're minimizing disk I/O. Imagine storing a binary search tree on disk. Every node might live on a different disk page. Searching for a single key could require dozens of page reads, and disk I/O is orders of magnitude slower than memory access. B-trees solve this problem by aligning the data structure with the storage medium. Instead of storing one key per node, each node, typically the size of a disk page, often 4 or 16 kilobytes. That means a single node can hold hundreds of keys and hundreds of child pointers. Because every node has so many children, the tree's fanout becomes enormous. A B-plus tree storing millions of rows is often only 3 or 4 levels deep. Looking up a record might require just a few page reads from disk. Another important design choice is that internal nodes don't store actual records. They only store keys and pointers that guide the search. The real data lives entirely in the leaf nodes. This allows internal nodes to fit even more keys, making the tree shallower. The leaf nodes themselves are linked together in sorted order. Once the database finds the first matching key, it can simply follow these leaf pointers to retrieve the next records. That's why range queries and ordered scans are incredibly efficient with B-plus trees. Insertion and deletion are also carefully designed. When a node becomes full, it splits into 2 nodes and pushes a separator key upward. When nodes become too empty, they may merge or redistribute keys with neighboring nodes. These operations keep the tree balanced automatically. The brilliance of B-plus trees is that they are built around the realities of storage hardware. They trade a little extra complexity in memory for dramatically fewer disk reads. That's why decades after their invention, B-trees remain the default indexing structure in relational databases and one of the most important data structures in system design.